You're welcome back to my YouTube channel. I am Moses Oluwasegun and this is Programmed Mathematics. So in the last video, I explained the inverse of a matrix, and particularly I discussed the part of 2 by 2 matrix. All right, so in this video, I'll be talking about the inverse of a 3 by 3 matrix. Okay, now in the last video, for a given matrix A, okay, which has the elements A, B, C, D, okay, I told you the inverse for a 2 by 2 matrix can be calculated with using the same formula, a direct formula, which is 1 over the determinant of matrix A times, okay, the adjoint of matrix A. So the inverse of the determinant of matrix A here is simply A times D minus B times C. So this is AD minus BC, okay, minus BC. Then this multiplied by the adjoint. For the adjoint, the elements on the principal diagonal are switched. So A and D will switch position. D comes here, A comes down here. Then the B and C, okay, the elements of the principal diagonal will then be multiplied by minus 1. So minus 1 times C is minus C. Minus 1 times B is minus B. For instance, if I have matrix A as a matrix, 1, 4, 3, and let's say 10. Okay, so if I want to find the inverse of matrix A here, this is simply 1 over the determinant of matrix A. 1 times 10 is 10, minus 3 times 4 is minus, that's a 12. So 10 minus 12 is minus 2, times, we switch 1 and 10 positions. 10 comes here, 1 comes down here. 3 and 4 are multiplied by minus 1. So minus 3 and minus 4. So if you use the 1 over minus 2 to open up this bracket, so 1 over minus 2 times 10 will mean minus 5. That is 10 divided by minus 2. Then 1 over minus 2 times minus 4. That is minus 4 divided by minus 2. That is 2. Minus 3 times 1 over minus 2. That is minus 3 over minus 2. That's simply 3 over 2, which is 1.5. And then minus 1 over minus 2 times 1. That's minus 1 over 2, okay, so which is just minus 0.5. So straight from here, the inverse of matrix A here is this. Now in the case of a 3 by 3 matrix, we do not have a direct formula as this, like the one we have in the case of a 2 by 2 matrix. So we need to follow the proper step in getting the inverse of matrix A. And what are the steps again? First, obtain the determinant of the matrix. Second, obtain the cofactor matrix. Then the third step, we transpose the cofactor matrix to give us the adjoint of the matrix. All right. This one you have in bracket is not a must. You put this in bracket. There's no reason for that. Okay. So it's just multiplication here. Then once we have the adjoint, we divide the adjoint by the determinant of the matrix. So let's take an example on this. Let's take an example on the inverse of a 3 by 3 matrix. So as an example, we want to find Q inverse if matrix Q is the set of the elements 1, 3, 0, minus 2, 4, 5, 6, 3, and let's just say 7. So this is matrix Q. So the first thing we need to do is getting the determinant of matrix Q. Okay, so we get the determinant of matrix Q. So Q is the matrix 1, 3, 0, minus 2, okay, 4, 5, 6, 3, 7. Okay, so you can pause the video to calculate the determinant of this matrix yourself. Okay, and then from there, you can continue from there to see if your determinant is correct. And then after that, you can pause the video also to obtain the cofactor matrix. Then continue to see what the cofactor matrix will be and so on. All right, so let's find the determinant of matrix Q. So I'm going to make use of the first row. The sign convention for first row, remember the first sign is always positive, followed by minus, then positive. So plus, minus, plus. So for 1, I have plus 1. Multiplied by the determinant of the leftover matrix. Row 1, column 1 will be deleted. So we have 4, 5, 3, 7, 4, 5, 3, 7. Okay, then minus 3. Okay, then the minor of 3, that would be minus 2, 5, 6, 7. So the leftover submatrix there, minus 2, 5, 6, 7. Okay, plus 0. Okay, so for 0 now, the sign convention is positive, so we have plus 0. Delete the row and column that 0 belongs. So our left is minus 2, 4, 6, 3. Minus 2, 4, minus 2, 4, 6, 3. And so from here, we can find the determinant straight now. So this is plus 1 times 4 times 7 is 28. 28 minus 15. 28 minus 15. So that will give us 13. So this is 13 here. Minus 3 bracket. Minus 2 times 7 is minus 14. 6 times 5 is 30. Okay, so minus 14 minus 30. That's minus 44. Okay, then plus 0 bracket. Minus 2 times 3 is minus 6. 6 times 4 is 24. So minus 6 minus 24, we have minus 30. So if you open up this now, here we have 13. That's plus 1 times 13 is 13. Minus 3 times minus 44. 44, 3. Okay, so this is 12. 12 again, that's 132. So minus times minus is plus. So this is plus 132. And of course, 0 times minus 30 is 0. So if we simplify this here, 13 plus 132 will give us 145. 145. So the determinant of matrix Q is 145. Then the next thing now is to obtain the matrix of the cofactors. So let's get the cofactors now. Okay, so this is a 3 by 3 matrix. So our cofactor also is going to be a 3 by 3 matrix. And so we need C11, C12, C13, C21, C22, C23, C31, C32, C33. So C11 here. The sign convention, don't forget as well, plus, minus, plus, minus, plus, minus, minus, plus, minus, plus. So this will give us plus M11, that's positive, M11. So we need C12. C12 also will be, that is for second row, first row, second column, the sign is negative. So this minus M12. So C13 now. C13, the sign is positive, so this is plus M13, M13. Then C21, C21, the sign convention is negative, so minus M21. We'll get all this later. Then C22, okay, C22, that is, the sign convention is plus, so this is positive M22. Then C23, the sign convention is minus, so this is minus M23. Then C31. The sign convention for C31 is positive, so this is plus M31. Then C32. The sign convention is negative, so this is minus M32. Okay, then the third one, which is C33. Okay, so I'm going to leave this because we need it here now. So C33 is, the sign convention is positive, so this is M33. All right, so once we have that, so all we need now is to get the minus. M11 means delete first row, first column. So let me get rid of these signs from here now. We're done using these ones. Okay, so we can delete them out. Now, row 1, column 1 deleted. We're left with 4, 5, 3, 7. So find the determinant of the submatrix here. So 4 times 7 is 28. 28 minus 3 times 5 is 15. When we subtract this, this will give us 13. So this is 13. Then for M12, M12, first row, second column deleted. First row, second column deleted. The submatrix left is minus 2, 5, 6, 7. So minus 2 times 7 is minus 14. 6 times 5 is 30. So minus 30. So this is minus 44. So this is minus, bracket minus 44. And that will give us positive 44. Then M13 is saying first row, third column. First row delete, second column, third column delete. So we are left with minus 2, 4, 6, 3. Determinant of that, minus 2 times 3 is minus 6. Okay. 6 times 4 is 24. So minus 24. Minus 6 minus 24 is minus 30. So this is minus 30. Then for M21, M21 is saying second row, first column. Second row delete, first column delete. We are left with 3037. 3 times 7 is 21. Minus 3 times 0 is 0. 21 minus 0 is 21. So this is minus 21. The minus is together with this one here. Then for C22, that was M22 here. Second row, second column. Second row, second column. Delete those two. So we are left with 1067. 1 times 7 is 7. 6 times 0 is 0. So 7 minus 0 is 7. Okay, so this is going to be 7. Then for C23, which is minus M23, M23 means second row, third column deleted. Delete second row, delete third column. All right, so we're left with 1, 3, 6, 3. 1 times 3 is 3. 6 times 3 is 18. 3 minus 18 is minus 15. So this is minus 15. And that will give us positive 15. Okay, so that's for second row, third column. Now, M31 is third row, first column. Delete those two. Third row, first column. So we're left with 3045. 3 times 5 is 15. Okay, so we have 15 minus 4 times 0 is 0. 15 minus 0 is 15. So this will give 15 here. That's M31. Now M32, third row, second column. Delete those two. Third row, second column. Delete them. So we're left with 1, 0, minus 2, 5. So if you find the determinant of the submatrix left, 1 times 5 is 5. Okay, third row, second column, 1 times 5 is 5. Minus 2 times 0 is 0. So we have 5 in this case. So here there's a minus. So together we have minus 5. All right, so and the last part of it is the third row, third column. Okay, which is M33. Third row, third column. Third row here, third column here. So we're left with 1, 3, minus 2, 4. 1 times 4 is 4. Minus 3, minus 2 times 3. Okay, 1 times 4 is 4. Minus 2 times 3 is minus 6. 4 minus 6 will give 4 plus 6, which is 10. So in this case here, we have 10. Now we have the cofactors complete. So let's get the cofactor matrix, and that is C equals, okay, so we form this line to the matrix. C11 is 13. C12 is 44. C13 is minus 30. C21 is minus 21. C22 is 7. C23 is 15. C31 is 15. C32 is minus 5. C33 is 10. So we have the matrix of the cofactors. Now, the next step here is to get the adjoint of the matrix. The adjoint of the matrix. Now, for the adjoint of matrix here, okay, so the matrix we have is matrix Q. All right, so adjoint of matrix Q, therefore, will be equal to the cofactor of matrix Q. Okay, transpose it. So we transpose this. So transpose the cofactor, transpose. So here, transpose this. First row becomes first column, second row becomes second column, third row becomes third column. So first row here, we have 13, 44, minus 30. Second row, minus 21, 7, and 15. Third row, we have 15, minus 5, and 10. So this gives us the adjoint of matrix Q. Now, then the last part of it is getting the inverse of matrix Q. So if we are to get the inverse of matrix Q, don't forget the determinant is 145. Determinant of Q is 145. Let me put it there. Okay, so to find the inverse of matrix Q, we simply divide the adjoint by the determinant. So we say therefore inverse of matrix Q, that's Q inverse, is equal to adjoint of matrix Q divided by the determinant of matrix Q. So determinant of matrix Q is 145, so 1 over 145 times the adjoint now, which is this. So we have 13 minus 21, 15, then 44, 7, minus 15, minus 30, 15, and 10. So this gives us the inverse of matrix Q. Now don't forget, this is simple scalar multiplication. So we can decide here that we open the multiplication. So to do that, we simply multiply 1 over 145 by each element here. And if we do that, this is 13 over 145. This is minus 21 over 145. This is 15 over 145. This times this, that's 44 over 145. 7 over 145 minus 5 over 145 minus 30 over 145, 15 over 145, 10 over 145. So now it's possible you reduce some of these fractions to their lowest term, but that is not a must. Okay, so you can only do that if you have multiple choice question where the fractions are reduced to the lowest term. So if you cannot find this, as long as what you have is very correct, if you can't find this, then reduce each of the fraction, okay, to the lowest term. So if you reduce each of the fraction to the lowest term, then if you have a multiple choice question, you definitely should have that answer there. Okay, so when it comes to calculating the inverse of a 3 by 3 matrix, is as simple as it is. First step, remember, get the determinant of the matrix. Second step, obtain the cofactor matrix. Third step, obtain the adjoint of the matrix, which is the transpose of the cofactor matrix. Then once you have the adjoint, then the next step is divide the adjoint of the matrix by the determinant of the matrix. All right, so it's a simple scalar multiplication there. So once you have that multiplication done, then you are good to go. Then it shows you have calculated the inverse of the matrix. Now, don't forget what I said. The moment we are able to get the inverse of a matrix, okay, it tells us that any system of equation that can be formed with that matrix can also be solved. Now, it's important to note this. When a matrix is singular, the inverse does not exist. The inverse does not exist. Okay, so look at this. For a singular matrix, okay, the inverse does not exist. The inverse does not exist. So what that tells you is that The moment a matrix is a singular matrix, it does not have an inverse. Remember, by singular matrix, we mean the determinant of the matrix is 0. So if, for instance, now look at this. If matrix A is singular, then what that means is that the determinant of matrix A is 0. Now, if we have that, then A inverse is what? The adjoint of matrix A divided by the determinant of matrix A. So in this case here, yes, the adjoint of matrix A will definitely exist, irrespective of whether the matrix is singular or non-singular, okay? It has something to do with the determinant. But in this case here, when the determinant is 0, this is over 0, all right? What you have here is an undefined fraction. This is an undefined fraction. So this tells you that the inverse of such a matrix A, whose determinant is 0, is undefined. In other words, it does not exist. All right? So whenever a matrix is singular, the determinant does not exist. And of course, I've told you also, one of the ways by which, apart from maybe other elements being non-zero, if a row or a column of any given matrix is all zeros, a row or a column of any given matrix is all zeros, then the inverse of such a matrix also will not exist, because the determinant is going to be 0. So the matrix is going to be singular. If I have a matrix, for instance, as the 0, 0, 1, 4, 7, 3, 8, 9. This is a matrix here. You can see this row here has all the elements being zeros. So if I'm going to take the column 1, the row 1 here to find the determinant, this automatically is going to be equal to 0. 0 multiplied by its own minor, 0 plus, then 0 multiplied by the minor, 0 multiplied by the minor, all that will be equal to 0. So if you have a given matrix as this, the determinant will be equal to 0, so the inverse does not exist. All right? The same, if the column is what you have, any of the column here also to be 0, 1, 4, 7, 8, 9, 10. This as well will give us a determinant of 0. So the inverse does not exist. Okay? So that's exactly what we're saying here. So it does not matter whether it is row 1 or column 1 that is all zeros. As long as you have any of the rows or column being zeros, so the determinant also will be equal to 0. So in that case, the inverse will not exist. All right. So in the next video, I shall be explaining how to use this matrix method to solve systems of consistent equations. Okay. For those who are math major at the advanced level, you will understand when we say consistent here, it means that the number of equations we have correspond with the number of variables available. So if I'm to solve a simultaneous equation having 2 equations, then I'm expected to have two variables. So in that case, I can apply the matrix method to solve the problem. If it's a 3 by 3 problem as well, 3 equations, then you have 3 variables. All right. So in the next video, I'll be explaining that. So we take it one after the other. So please, if this is your first time of coming in contact with this YouTube channel, please subscribe to my YouTube channel. At the same time, please recommend the channel to your friends and everyone around you. Like the videos, give me thumbs up on the videos, and at the same time, use the comment section to reach out to me. Okay, so please, let's see in the next video.